So here's the state of affairs. We believe the following. We believe that P does not equal NP. And what does that mean? That means a whole host of problems that we wish we could solve fast can't be solved fast, right? There are things that we want to know the answer to that we think we probably can't get the answer to in a reasonable amount of time. That's too bad, right? This is a sad face kind of a belief. This is a pessimistic view. It's probably an accurate view. Right? It's generally accepted to be probably an accurate view, but it's too bad, right? We want to be able to solve these things fast. So here's the thing. So we could think of two potential goals in our search for good algorithms. The goal that we've had so far, here, let's just do it like this, 2 goals. The goal that we've had so far is we've said we want the right answer, right? Whatever it takes. We want to design algorithms that are guaranteed to give us the right answer. So here what we think about is we could say we're going to require optimal or require correctness as long as it takes, right? No matter how long the algorithm takes, right? No matter how slow. So the problem with this is that it appears that this can require us to wait a very long time. So recall the Held-Karp algorithm. So this was the DP algorithm for the TSP, the optimization version of the TSP. The Held-Karp algorithm takes n squared times 2 to the n time, right? So it is a big theta of n squared times 2 to the n, which is not a good deal, right? That is a slow, very badly scalable algorithm, right? So here again, we've got a sad face, right? So this is a bad deal. If we require optimal answers, we're going to have to wait a long time. And in fact, we don't need very large problems before we apparently need to wait longer than the age of the universe, right? There are actual things we can't do here. The other possible goal, right, if we're unsatisfied with that goal on the left, the other possible goal is to require something else, right? Our other possible goal is to require fast algorithms, right? So require speed. And in requiring speed, we might actually have to lose something on the optimality front, but maybe it's worth it, right? Maybe we don't have to give up that much. So on the left, we say we're going to require optimal solutions, no matter how slow. On the right, we're going to say we're going to require speed. And then our no matter then is going to be something like no matter how bad the solutions get. Or, we could phrase this in a positive light and we could say require speed and then get as close to optimal as possible, right? So get as close to optimal as possible. Okay, and I can't draw a smiley face that does this, but maybe what we'd like is a smiley face that does something like this. Is this possible, right? So there's our question face, right? Maybe we could do something here. And so to begin this study, let's look at the TSP. So you all remember the TSP, right? TSP says given n cities and the distances between them, what's the optimal Hamiltonian circuit or what's the minimum cost Hamiltonian circuit on the graph? Or what's the best tour of the cities that visits every city exactly once, and we call it best from the standpoint of shortest total distance. So here's an example graph we'll use in this study. So we're thinking about TSP. We're asking, could we just solve the TSP fast and get somewhat close to the optimal solution? All right, so TSP is going to look like this. I've got A, B, C, D, A, B, C, D. I will have edges with a cost of 2 in these 2 spots. I'll have edges like this, 1, 1, 1, and I'll have an edge like this with a cost of 9. All right, so I'm going to call an optimal solution to this TSP instance. I'm going to call that by a name. I'll call that opt. Okay, so opt means an optimal solution. Okay, so it turns out that an optimal solution for this instance is one which avoids the 9. Okay, so if we avoid the 9, how do we do that? Well, we go something like this, right? And I'll color code this just a bit. So we go like this. Okay, so that is an optimal tour of this, right? And so I'll color code optimal here in green, and we can ask what's the cost of opt. Well, the cost of opt is equal to, in this particular instance, 6. Okay, and I can write opt in a variety of different ways, but here I can, writing A, B, D, C, A is fine. So this is A, B, D, C, A. Okay, so there's our picture of kind of the best thing that could happen. And so now let's do something else. We know that we can't find the optimal without doing exponentially a large amount of work. So let's kind of tinker with something else. Let's think about what other kinds of algorithms would let us find a solution fast. Okay, and I think the easiest one to start with conceptually is a greedy algorithm. So how does a greedy algorithm work? So let's think about a greedy algorithm for this. So we'll call this the local greedy algorithm. Local greedy. How is it going to work? We'll start at A. Start somewhere arbitrary, but A is fine for our purposes. Go to closest node, and then repeat until we've visited everybody, then go back to A. Right, this happens until we're out of nodes, and then we return to A. So let's use red, the ominous red color, to denote the greedy solution here. Okay, so how does our greedy algorithm work? Well, we're gonna investigate it here. So we start at A, and then we take the shortest route that's available to us, right? So what is that? Well, that's this one. So that's a good sign, right? That's part of the optimal solution. That's looking good. And now once we're here at B, we have two choices, right? There's only two nodes left that we haven't visited, so there's only two choices. The first choice is to go to C with a cost of 1. The second is to go to D with a cost of 2. What's the shortest route? Well, it's C. So we go to C with a cost of 1. And now there's only one choice left, so we have to do it, right? That one cost left takes us over to D. And now we're stuck, right? We're stuck. We've essentially tricked ourselves into taking that edge that costs 9. Okay, so now what's the cost of a greedy solution? Well, let's add ourselves some notation here. So we're going to say G is the algorithm. Now that's the greedy algorithm. That'll be the name of it. And then we'll say XG is the solution found by the greedy algorithm. By G. And so what did we just find? Well, we found that the cost of XG is equal to 12, right? And so what's the 12? Well, it was 1, 1, 1 plus 9, right? So 3 plus 9 is 12. Okay, so that's not good. It's twice as bad as the optimal, right? And we can just, for completeness, we can write XG here equals A, B, C, D, A. Is that correct? So A, B, C, D, and then back to A. A, B, C, D, A. Okay, so that's XG, and we'll color code it all in red. Okay, so that looks fairly bad, but it's not obvious that it was horribly bad, right? This maybe we could make the claim that somehow this is close. Like if we can always get within 2, that might not be so bad.